Hello community! Let's start with a title and we will prove this title either wrong or right. So you know what is the beauty of our models here, like Q1, QWQ or DeepSeek R1 or Gemini Thinking? We can watch them think in detail. So let's open here this discussion and we can see those AI model, how they explore different reasoning options. We can see how they follow different paths of causal reasoning, and we can understand the complexity level that each model is able to achieve in their exploration, searching for an answer to our queries. And you see this live, if you want, here, this reasoning process in my last video, also the videos I did in DeepSeek R1. And then there was a spark of genius. You know why? Because suddenly some scientists understand, hey, we can improve our AI system, we can improve their reasoning capabilities significantly. And you might say, yes, of course, there was just yesterday this beautiful publication, January 31st, Think Smarter, Not Harder. And you remember, this is here the Inference Budget Constraint Policy Optimization, where Meta said, hey, we built something for adaptive reasoning during inference. But just 2 days ago, I showed you this video that is much simpler, also about a test time optimization, but now instead of a DPO, we also have a test time preference optimization, which is much more elegantly. Why? Because here, this latest paper from Meta here, they are about an inference policy optimization by a budget constraint. And in a nutshell, if you want to understand this, they say, well, models fine-tuned through our methodology learn to understand the difficulty of queries. This is what I call the complexity level. And then this model allocates inference budgets to the harder problems, to solve the harder problems. And you know what? Maybe I can show you that this might not be a solution at all. So, in itself, the paper of Meta is nice. They have this idea of a stochastic optimization, which is really beautiful, and they go on how to practical update here everything, and they have semi-gradients and whatever. Great, yeah. But you know what? No, I was talking about another spark. Sometimes ideas are simple and beautiful. You don't have to do this mathematical, and then it might find out, hey, it is not even working. So, because, and this is the simple beauty, we can watch our AI models like R1 thinking in real time. We find that those inference compute models underthink our query. So what does this mean? Let's come to the core of this video. And you might say, hey, do you mean that this 2-minute test time compute is not long enough? Well, remember, this is not a chat model. We are using this model to solve complex problems, to calculate certain molecular compounds. Therefore, I don't need a reply by the system in 1 second time. If it takes 5 minutes, it's okay for me. If you ask a pharma company, hey, is it okay if I take an hour? They would say everything that is below, 5 years is gorgeous. So we are here solving complex problems. Plus, remember this. So here we are. This is now DeepSeek, and I simply ask you, DeepSeek R1, hey, if I think about here, dark matter and dark energy, how do you structure this? And I just wanted to show you the ideas. And this is here the thinking process, not the answer. And we watch here the system think. And it says, hey, maybe there are alternative theories like the modified Newtonian dynamics, the MOND, which is beautiful in itself, the idea. And then R1 tells us, hey, I need to structure those thoughts. I have to list here the evidence of dark matter, the galactic rotation curves, the gravitational lensing, CMB observation, galaxy cluster collisions. This might explain, and then R1 comes, but wait, I should verify at each point. So for the rotation curves, do all galaxies show this discrepancy? How precise are the measurement? And for gravitational lensing, how do we map the mass distribution? And also particle physics, you see, a complete other idea from the other end of theoretical physics, particle physics experiment. You have here this weakly interacting massive particle. The WIMP particles have definitely detected dark matter particles yet. So putting it all together and you see what is happening. We have a lot of ideas, and then everything is put together, and everything then, the AI system tries to condense an answer. So let me give you a visualization where I try to show you how easy it is to come up with a solution. You see, those are our 5 ideas here. 1, 2, 3, 5 blue arrows, 1, 2, 3, 5 blue arrows. And this here is the depth of thinking, the reasoning. How deep is the thinking happening? And you see, well, they're about more or less all somewhere here at the same level, yeah? But you know what? If we want to find the real solution, maybe it is here not the first solution, but the second sort. And then we have to go what the authors call deep reasoning to reach the correct solution. And remember, this is not a chatbot. I don't need an answer in a second. I need an answer in an hour. But I need the correct reasoning process for a molecular property or for some financial transaction or financial risk assessment. I need the complexity that is happening. And currently, our best models, our QWQs, our O1, our R1, our whatever Gemini thinking, they seem to be here on this left side idea. So how do we achieve that the model are here? And you might say, but how do we know that this is the right one? No? You know, there's a funny idea. And the authors thought about this and they did some experiment and they came back and said, you know, a notable proportion of initial thoughts across various models were correct, but were not pursued to completion. So of initial thoughts, so let's say this is our second initial thought, and this would have been the correct one, but they were not pursued to completion. And the authors write, this tendency to abruptly shift away from these promising thoughts and go to the next one indicates here an inadequate depth of reasoning where potentially correct solutions are prematurely abandoned before being thoroughly explored. Now, this is amazing. So this means the system R1 found the right solution, but somehow something in the system said, you know what, let's jump to the next one and jump to the next one. So we have a wide array of possible solutions. So we have a huge exploration, but the exploitation of the good one is not happening really, as I showed you in my video about the new improved Monte Carlo tree search adaptation methodologies. And you might ask, why is this not happening? Well, one of the reasons immediately clear is, no, this behavior reflects deeply into training data sets. You know, the data, it is the most important whatever for our AI systems to learn. But let's come to the fact of today. This is the study I would like to show you, thoughts all over the place on the underthinking of O1-like LLMs from the last days of January 2025. Now, of course, remember if we talk about here open-ended question, you could interpret statements. So what the authors did, in order to get good results that we can validate easily, we focus now on science and we focus on mathematics because we can immediately validate if this is a correct mathematical solution or not. What a beautiful idea. We know from O1, from the publication by OpenAI, we have here the train time compute, the log scale here, if we take more time, and then the test time compute, how the performance goes up. So we have here the O1 data, but we don't know the reasoning process because O1 is closed, a proprietary system. We are not able to learn. Only OpenAI, the staff of OpenAI, is able to see this. And if we look here, we see just here PhD level science question of physics here. With GPT-4 Omni, we went up to 60%, but now with O1, we are above 90%. And this learning, this is what we are focusing now, and this is what we're going to improve now to have even a better performance. Let's look at a benchmark test that did here our authors. A beautiful idea. We have here in blue the number of the thoughts the AI system had, and in red you have the number of tokens in thousands. So you see, if we have here a mathematical 500 test set, never mind what it is, a simple mathematical test, and we have a level 1 to level 5, and level 5 is difficult level. And we just have a look at the number of, let's start with the number of thoughts. This is the blue line. So you see, the more difficult the mathematical equations get, the more sorts an AI system would need to solve it. Sounds simple, no? The number of tokens. The more complex the red bars, the more complex the question are, the more token will be included in the computation of the answer of the query. We have this with QWQ32B. From my last video, we have this DeepSeek R1, the preview version. This was a month ago. Then we have the real R1, now the final version, the 671 billion pre-trainable parameter mixture of expert system model. So you see, it is almost a similar characteristic. Interesting, you can compare here the preview model to the pure model, but more about this in a later video. So what they did, they said, hey, my query is a simple mathematical function. Never mind what it is. And the system comes up now and says, R1 comes and says, okay, I have my sort 1. So I've got this problem here and it involves some equation with some variables a, b, x, y, z, and maybe I can go this way. Or sort 2, alternatively, maybe there's a geometric interpretation. So maybe I should look at the problem from a geometric point of view. Or sort 3, alternatively, says R1, perhaps the problem is that for some set of x and y, both equations hold simultaneously and I find an a and b such that, or sort 4, perhaps I can go another way, and you see the multitude of possible sorts. And now the authors did something beautiful. They said, okay, let's count now the tokens for the correct response in green, and let's count the tokens for the incorrect response. So what is happening here? Here you have for the mathematics and here for a science problem, never mind, characteristic is the same. You found here our 3 models. The correct response needed below 3000 tokens, but the incorrect response went somewhere to about 10,000 tokens. So this system generates tokens like crazy before the AI stops now in its incorrect reasoning path because somehow it gets it that it does not find here a solution. So it spends here quite an amount here of token, of time, of energy to search, but it does not come to a conclusion. So all the energy and the time wasted might be not to find the correct solution, but to run around like crazy in a circle with incorrect responses. And you can see this pattern all over the place. So this was interesting for the authors as a starting point. And then they say, okay, so we leverage LLMs to assess whether each sort leads to a correct answer using the following prompt, and this is the prompt, and beautiful. And what's nice, they used here really the latest distilled model. You see DeepSeek R1, the distilled Llama 70B, and the DeepSeek R1 distilled version Q132B here for this evaluation. Never mind, you can read this, but this is not important. Important is another fact. Look at this. This on the x-axis, we have the ratio of the correct sorts to the distribution. And this here tells us here that over 70% of the incorrect responses contain at least one correct sort in the chain of thought and the reasoning structure. And in more than 50% of those incorrect responses, over 10% of those sorts were correct. So it is not that everything is wrong. It is amazingly a high amount of correct ones, but those are not activated. Or one-like models can initiate here the correct reasoning pathways. They may struggle to continue those correct pathways to reach the correct conclusion. And now the most interesting question is, why does this happen? Yeah, there's an easy solution, and the author of the study gives us here an easy solution. Yeah, let's have a look at this. So, in standard decoding, the probability of each token at position t is computed using the softmax function over our logits. Beautiful. So if z are our logits, our unnormalized score for the tokens, by repeating this step, we have a next token prediction, an autoregressive LLM. You understand what's going on. We generate here a linear sequence of token, and we have now simply we have a sort switching penalty that we impose on the system. So we say, hey, system, Don't jump to the next thought. Stay with it. And we have two parameters, the penalty strength and the penalty duration. Rather easy formula. But I think it's one solution, but I'm quite sure this is not the real solution that gives us here the jump in the improvement. Because what they do, they simply go here for the logits here and then they just look at those and says, hey, for example, the word alternatively. No, Art1 told us, alternatively, I can look now at this system or alternatively. So whenever you see here this word, you can say, hey, wait a minute, R1. Yeah? Continue your reasoning pathway a little bit more down. Maybe you found a solution. But I was talking about why, and I think this is the most important question here. Why does this happen? Why has nobody noticed this before? It is all, of course, on the training data. So let's have a look. LLMs are trained to mimic the human text, which often includes exploratory reasoning, brainstorming, whatever. However, human problem solving typically converges on a solution after the exploration, while our LLM model lack here this mechanism to prioritize here a convergence. We don't show the models in the training data what we expect them to do. We hope that there is somehow a little ghost in the AI machine, a little genius, a little genie that says, now I understand. Yes, I have those and those and those data, and now I mix up some mathematical solution to this. This is not the way it's gonna be. So the training data may now emphasize the importance of completing a reasoning path once started, leading here to superficial exploration. What we have is a lack of explicit reward for going for a deeper reasoning structure in the argumentation of our O1, R1, whatever. So those reinforcement learning tuned models like O1 are optimized for the final answer correctness in the reinforcement learning, but not for the reasoning efficiency and not for the path coherence. And you might say, how is this possible? But yeah, of course, look at the data sets that we have, the training data sets. And the authors come and say, hey, this creates a disconnect. The model knows what to solve, but not how to structure the solution in the optimal way. So we have now to generate data sets that we can train those models again on this new data set, where we not only show the model what to solve, but exactly how we want the solution to play out in the internal reasoning system. It is so easy to understand, but somehow it's so complicated to put this to work. A little bit more text if you want to have a little bit deeper dive, decoding strategy bias towards exploration. We understand we are looking here only in a high probability immediate token linear sequence, of course. So whenever the system encounters now a probability between the next deep token or the token, hey, alternatively, I could switch to another sort, maybe the probability, the logit for such a transition token might be high enough to trigger here a premature shift to the next solution and not finish the first thought. In the standard decoding lack here the penalties for abandoning thoughts early. So the model, if you want, jump ship to a new path without costs and so easy to solve, So short-term token optimization. LLMs generate tokens sequentially. LLMs are currently optimized for the local coherence for the next token likelihood rather than a global reasoning quality. And this is where we can change this easily with the training data sets. Now let's come back to if you only provide computational resource allocation, like the article by Meta that I showed you at the beginning of this video. Let's think about this. If Meta tells us, hey, we just need to provide more resources to more complex problems. And you might say, of course, this is a solution that is clear, no? But what we just went through, if we don't change here the training data itself, that we show the model how we want it to be solved, and we want it to go down 10 levels, 12 levels, 15 levels of complexity to find a solution, it is not just more computational allocation of the resources, but it is about the way how we teach the systems. So therefore, I think, I am not sure if Meta, maybe it has part of the solution, but I think it's missing out here on this important problem. Yeah, we talked about this. So the next logical token might have a lower probability than a transition phase like, hey, let's jump to the next idea. This sort switching penalty, this tip idea, the simplest form, real nice, works. So let's have a summary. This abandonment of correct early thoughts. So the system is there, and the system is in the first 3-5 attempts, there is the right solution. But it's not due to a lack of capability of the system. We do have the compute power, but rather it is a systemic bias in the decoding algorithm and the training data that simply prioritizes here a wide array of exploration over a deep dive here in the reasoning process. So again, we have here, like in Monte Carlo tree search here, exploration versus exploitation. And one of the open questions I'm currently thinking of, how can I take this system here and integrate here Monte Carlo tree search in an adapted, in a little bit more advanced way, that Monte Carlo tree search is taking care about this? I don't know yet, but this is just an idea for the night. So, summary, by explicitly penalizing here through switching behavior, this tip methodology kind of recalibrates the model reasoning process to align with human-like persistence, addressing here the root cause of this underthinking that is happening in our O1, R1, QWQ, and Gemini thinking model, because neither of those models achieves 100% correct behavior. And this now brings us back, and I made a mistake. It is not that the model is stupid. It is that I'm stupid. That us as coders, people who build those systems, I don't know why I did not thought about this, seeing this reasoning progress and seeing that somehow then all those ideas are pooled together and then comes one solution out here in the output of the AI system. And what happens to all the other pathways? My goodness, there's so much still to learn, but I think it is amazing how simple sometimes the idea and the approaches are from the AI scientists to improve the reasoning capabilities. And they tell us here, and this is the end, our empirical result tell us the authors demonstrate that with this, for example, tip methodology effectively reduces the underthinking and it enhances the accuracy across difficult mathematical and scientific problem sets without additional model training. So this is the beauty. This tip methodology, you don't have to train anything anymore. You don't have to modify. You just have here with two hyperparameters. You tweak a little bit here if you want a probability density that you have a little bit more of, I would not call it a global coherence, but you are not only strictly bound by a local coherence for your next token probabilities, but you are looking a little bit more ahead to a deeper reasoning chain of thought structure like this. So I think there are a lot of other solutions. I have two other solutions in mind, and maybe you also have one, and maybe you can code it immediately and find it and publish it. How interesting is currently here, this time of year, the end of January 2025 in AI. I find it fascinating. I hope you enjoyed this video a little bit. I just wanted to show you this. I have my own thoughts about how we can even improve on this one. So maybe you want to subscribe and maybe I see you in my next video.